to say makes sense for general topological spaces. So let Xt be a metric space. We say that X is connected if the following is impossible. And after I've written this down, I'll draw some pictures and show you what this means. X can be written as the union U union V of two open sets so that they are disjoint and both are non-empty. So what these open sets are doing really is separating X into two distinct chunks. So it's based on these pictures. So for example, if this is U and this is V, then U union V is not connected, because we've got two disjoint, non-empty open sets that make up our metric space. Another example, which we'll prove in a moment, is that the unit interval 0, 1 is connected. It's impossible to break the interval 0, 1 into two disjoint open sets unless one of them is empty. So, and intuitively we feel that the unit interval is kind of one indivisible chunk, whereas this one clearly is not.
This is kind of interesting, but 0, 1 is closed, so can you actually write it as the unit of two open sets?
Yes, well, we're treating that as our universe. That's our metric space. Right, so this we could write, for example, as 0 to a half union 1/4 to 1. These are open sets in here. Okay, but of course they have overlap. And the problem is that however you write the first one, when you get to the end of it, it will have to be included in the other set, but at the same time that will force some overlap here. That's the basic idea. Okay, so let us prove that this interval is connected. Any A and B, the closed interval A to B is connected. write this closed interval a to b as u union v where their intersection is empty and both u and v are non-empty. Now, one of them has to contain A. So at the cost of relabeling them, we can assume that U contains A. So let us assume that A is in U. Now, because U is open, U must contain a ball centered at A, and so there is some delta greater than 0, so that the interval from A to A plus delta, open on the right, is completely contained in U. So what we're going to do is we're going to move from left to right, starting at A, and we will only stop when we finally encounter a point from the other set, V. So let S be the set of x's with the property that the closed interval, or rather the half-open interval from A to x, is completely contained in U. What can we say about S? Well, S contains A plus delta. So it's not empty. And also, it is an interval because if you have a point x in there, then any smaller number will also work. S is an interval. Now we're looking at numbers that are bigger than A, and consequently S has the form open interval A to C, or the half-open interval A to C for some C below B. Now let's look at that point C. I'm going to claim suppose that C is equal to B. Then U contains all intervals of the form A to B minus 1 over n, for n greater or equal to 1. And since it's an open set, it's going to contain the union of these. So U contains the open interval A to B. But now where is B? The other open set is non-empty. So far, all the points we have are in U. So since V is non-empty, it will be the case that B is in V. But again, V is open. So it contains an interval that looks like this. B minus alpha to B for some alpha greater than 0. But now that number, B minus alpha, it's strictly to the left of B, so it's in U. And it's also in V. And what we have here is a contradiction, so this is impossible. Under the assumption that U and V have disjoint overlap.
B minus alpha is not in V because it is.
Sorry?
B minus alpha shouldn't be in V because it is half open, right?
Well, in our set, this counts as open. It's relatively open. Okay?
Yeah, I think he means that you're missing the left endpoint, which is B minus alpha. So B minus alpha is technically
sorry. Yeah, B minus alpha over 2. Sorry, I misunderstood your question. B minus alpha over 2 will be in the intersection. So we know that this point is not equal to B. So case 2 is when C is strictly less than B. And now we ask, where is the point C? So it could be in U. But because U is open, U contains a small interval of the form C minus beta to C plus beta. There's room for that because C is strictly less than B. But then we have that A to C minus beta over 2 is contained in U, and C minus beta to C plus beta is contained in U. goes there, that's in U, and then that bit there is also in U. So when you put them together, you find that the interval from A to C plus beta is contained in U, but this contradicts the definition of the set S, because S was as far as you could go and while remaining inside U. So contradicts the definition of S. So that's ruled out. So the second possibility is that the point C is in V. But then some small interval C minus gamma to C plus gamma is contained in V, since V is open. And so if I look at the point C minus gamma over 2, that is in U intersect V. Again, it's impossible because we're assuming that U and V are disjunct. Well, we've ruled out all the possibilities. And so, therefore, no such U and V can exist. And therefore, the closed interval from A to B is connected. So the argument just depends on finding a point where you transition from one of the open sets to one of the others. And then the fact that you can find a small open interval around that, it must overlap with U in one direction and overlap with V in the other direction. Well, we can use this as the basis for describing all connected subsets of R. We have not specified what our subset is. It needn't be closed or open or anything. So a subset E contained in R is connected if and only if it is an interval. Could be closed, half open, open, whatever. Infinite, semi-infinite. So we've got two directions to prove. So let's suppose that we have a subset and that it is connected.
does it mean for a subset of some metric space to be connected? Because the way that we've defined connected, it has to be capable of being written as the union of two open sets.
Right, within, so we have the relative metric. So whatever metric, well, we have the standard metric on R. When you restrict it to a set E, it creates its open sets, once you have a metric there.
Okay.
Okay.
So you just treat E as your universe and then apply the same definition.
Right.
Okay.
Okay, so let's go this way. Suppose that E is connected. Now, if it's not an interval, what's the property of being not an interval? It means you can find 2 points in your set so that between them there's a point that's missing. So, suppose that E is connected. If E is not an interval, then we can find 3 points, A less than C less than B, with A and B in E, but C not in E. So let's define U to be equal to E intersect with the interval minus infinity to C, and V is E intersected with the interval C infinity. Together they must make up the whole of E, because the only point we could be missing is C, but that wasn't in E to begin with. So since C is not in E, we have that E is U union V, with U and V open in E. Remember, the relatively open sets are those that you get by intersecting with open sets of your big metric space. Also, there can be no overlap because the first one lives in the interval minus infinity to C and the other one in C to infinity. So U intersect V is empty, and A is in U, and B is in V. So both U and V are non-empty. So in this way, we found a decomposition of the set E into 2 open disjoint pieces, both of which are non-empty. So this contradicts connectedness. So what did it contradict? Our assumption that E is not an interval. So therefore E is an interval. direction, let's assume that E is an interval. Now, we've dealt with closed intervals, but there are other types of intervals. We don't want to go through the same proof again, so we can deduce this from the closed interval case. So, suppose that E is not connected. So we'll derive a contradiction by assuming the opposite. Then there are open sets in E. So that E is U union V. The two sets are disjoint, and both are non-empty. So, since they're non-empty, we can take a point in each one. So take A in U, B in V, and we can assume that A is less than B, otherwise we can just interchange U and V. Then, because we have an interval, the closed interval A to B is contained in E. When I intersect U and V with this closed interval, what I get is two open sets in the closed interval A to B. We get that U1 and V1 are non-empty disjoint open sets in the closed interval AB, and because U and V made up the whole of E, U1 and V1 is the closed interval A to B. So we've just proved then that the closed interval A to B is not connected and consequently this contradicts what we just proved about the closed interval. So it contradicted our assumption then that E is not connected. Therefore, E is connected. So this characterizes nicely the connected sets in the real line. They're just the intervals Now, in making use of this, the following result is quite useful. So let xd and y rho be metric spaces. Let f from x to y be continuous. Then, if x is connected, we have that its range, f of x, is also a connected set. So we'll use one of our characterizations of continuity. Suppose that we can write the range f of x is u union v for disjoint open sets u and v contained in the range. In order to establish connectedness, we have to show that either u or v is empty. Now, by continuity, the inverse images of u and v are going to be open in the metric space X. They're also disjoint, and since f of x is the range of f applied to x, these are going to make up the whole of x. So when we look at the inverse image of u and the inverse image of v, are disjoint in x, because u and v are disjoint. And together, they must make up the whole of x. Now, we're assuming that x is connected. So if you have x written as a disjoint union of two open sets, the only possibility is that one of them must be empty. So since x is connected, one of these is empty. And therefore, one of u and v is empty. So that says that the only way that you can write the range as a union of two open sets is in a trivial manner where one of them is empty. image of a connected set is connected. So let's look at an example. In R2, let T be equal to the unit circle. So points where x squared plus y squared is equal to 1. This is a connected set, and the easiest way to see that is to use the previous result and exhibit the circle as the image of a continuous function from an interval. So define a function f from the closed interval 0 to pi to the circle by f of t is the point with coordinates cosine t, sine t. Letting t vary from 0 to 2 pi takes you once around the circle. It's not a one-to-one mapping because they meet up again at the point 1, 0, but that doesn't matter. So f is continuous. The range is the whole of the circle, and we've already established that any interval in the real line is connected. And consequently, the previous theorem, what was it, 3.4? 3.4. So theorem 3.4 tells us that the circle is connected. And again, it's intuitively reasonable. It's hard to imagine being able to break the circle into two open subsets, each of which is non-empty, and they are both disjoint. But rather than do some calculations, we can just use this theorem and get it immediately, just observing that it is the continuous image of a connected set. And so it stays connected. Okay, so we're out of time today. Next time I'll talk about something that's a little bit stronger, which is path connectedness. And let me remind you, homework's due on Monday.